In this video, we are going to cover section 10.2, which is called Exponential Decay. So, one of the good examples that relates to exponential decay comes from chemistry, and it deals with radioactive substances. So, a radioactive substance is not stable. So, over time, it transforms itself into another substance, and this is the process is called radioactive decay. And radioactive decay is caused by the interaction between nuclear particles, like protons, neutrons, and electrons, that are in that radioactive substance. So it makes sense that if you have a larger amount of radioactive material, it's going to experience more decay. So the more that you have, the more decay it's going to experience. And said mathematically, the rate of decay is proportional to the amount of radioactive substance present, just like we saw in the last section, where the rate of growth of a population was proportional to the size of the population. As a result of this proportionality, we can use the exponential model, y equals a times e to the bt, to model or describe exponential decay. And I just want to point out here what these variables or constants mean in the context of exponential decay problems. Y, a lot of times they'll use Q instead of Y, but Y here represents the amount of radioactive substance that is remaining. A represents the initial amount of radioactive substance, the amount that you began with. B is called the decay constant, and that's going to be different for every radioactive material. And T represents time. Depending on the radioactive material, time may be measured differently. So time may be measured in days, it could be measured in weeks or months or years, depending on the specific radioactive substance that you're working with. So let's look at our first example. I'm just going to sort of set up the example for you, tell you about this radioactive substance, iodine-131, and then we'll do the example. So it says, hospitals use the radioactive substance iodine-131 in research. It's effective in locating brain tumors and in measuring heart, liver, and thyroid activity. So what will happen here is you may have a patient, and you may even see something like this in your clinical hours once you get into the nursing program, those of you who are nursing students. You'll have a patient who is maybe receiving an ultrasound or an MRI or a whole body scan in this case, and they will inject them with this radioactive material because it's going to show up on those scans, and it's going to gather in the spots where in this case, where we have the cancer. All right, so on the left you have a picture of the patient, and you can kind of make out like the outline of their head, and then the trunk of the body in the middle, and then at the bottom you have the legs. So the picture on the left represents his scan before treatment, and then the picture on the right represents the scan after this patient has received some sort of treatment, maybe radiation or chemotherapy. And what they're looking for here is what you would like to see is that the dark spots sort of dissipate, so you have less dark spots, and that would mean the cancer is going away. And in this picture, the red arrow on the right, that's showing that you have that little dark spot there, which is where the cancer is still active. And then you can see, if you compare the before and after pictures, there's less uptake in the mid-pelvis area, which would mean that the cancer had gone away in that area. And then it's also, it notes that the dark spot at the bottom that's near the patient's leg, that's just the urine bag. So this patient has been catheterized while they were doing the scan. All right, so here's an example with iodine-131. It says, a hospital purchased 20 grams of iodine-131 And 8 days later, when a doctor wanted to use some of the iodine-131, he observed that only 10 grams remained, and the rest had decayed. So this would be something that you would have to think about if you were like a hospital manager or the person who orders these radioactive substances for our hospital or some sort of doctor's office. You would have to think about like how often are we using it and how much should we purchase so that the next time we go use it, it's not all decayed. So this question has two parts. Part A is going to be pretty difficult, and then part B is going to be really easy. You will not be expected to do a question like part A on the test, but I wanted to show you how we can develop mathematical models using information about iodine-131. All right, so let's start with part A. So it says, develop a mathematical model that represents the amount of iodine-131 present. So we already learned that we're going to use this exponential decay model, y equals a times e raised to the bt. Now let's figure out what we know. We said that y was the amount remaining, the amount of the radioactive substance that's remaining. A is the initial amount of radioactive substance. B is the decay constant. We don't know that right now. We have to find that. And T is time. So, and E, don't forget, E is just that number E. So that's not a variable, that's a number. So let's see what we know here. We know that initially the hospital purchased 20 grams. So that's going to be your value for A. We know that it decayed to 10 grams, so that's going to be Y. So A is going to be 20, Y is going to be 10. And we also know that it took 8 days for 20 grams to decay to 10 grams. So that tells us what the value of T is. So we know that A is 20, Y is 10, and T is 8. So let's plug those numbers in. All right, now you can see here that the only variable that we don't know is B, because remember E is a number. So we need to figure out how to get B by itself. So let's start by dividing both sides by 20. Get rid of that coefficient. All right, so that's going to cancel out on the right hand side. And then 10 divided by 20 is 0.5 or 1/2. And you'll notice here that I just rearranged the exponent. So instead of B times 8, I wrote it as 8B. And that's just because we're used to seeing the number come first and the variable come second. But you could have left it as B times 8. That's not wrong. All right, so now we have to do something a little bit fancy. And like I said, this is not something that I would expect you to do on the test, but I do think it's useful to see it. If you go on to an algebra class, you'll definitely have to do something like this. All right, so to get B by itself, we have to use the natural log. And the reason that we use the natural log is natural log and E are inverses, so they're going to cancel each other out, and that's going to make everything work out really nicely for us. So let's take the natural log of both sides. All right, so natural log of 0.5 equals natural log of e to the 8 times b. All right, now I told you before that natural log and e are opposites or inverses, so they're going to cancel each other out. All right, and then 8b is going to come out of the exponent, and you're just going to have natural log of 0.5 equals 8 times b. Now, natural log is a button on your calculator, so you may want to pause the video and take a second, find your natural log button. All right, now we're almost done. We almost know what b is. So to get b by itself, we have this 8 in front of it right now. So to get b by itself, we're just going to divide both sides by 8. That's going to cancel out the 8's on the right-hand side. Then you're left with b equals natural log of 0.5 divided by 8. And now we can plug this in our calculator. All right, so we have natural log of 0.5. Your calculator is probably going to open up a parenthesis for you here. If it does, you should go ahead and close it. And then divided by 8 is negative 0.0866433,976. So I just went ahead and rounded this to, let's see, I rounded it to 9 decimal places. Some of these problems on your homework, they want you to round to like an obscene amount of decimals. So I just wanted to mimic that in this video. So the value of B, which was that decay constant, is negative 0.086643398. Now, we're almost done. We just need to throw this stuff back into our mathematical model. So the only thing that's left to do is just to plug everything in. So we take our exponential decay model, y equals a times e raised to the bt, and you're going to plug in the initial amount, because that's going to stay the same always. You always purchased that same amount in the beginning. And the other thing that's always going to be the same is that decay constant. So we're going to plug in a equals 20 and b equals negative 0.086643398. And that's going to be our mathematical model. And there you have it. Y equals 20 times e raised to the negative 0.086643398 times t. That's your mathematical model. Now, the hospital can now use this mathematical model to determine, how long they would have to use up their iodine-131 before it's completely decayed. So they could plug in a different number of days. They could say, okay, well, how much is going to be left after 12 days, or how much is going to be left after 3 days? They could plug those values in for t, and this model would spit back out how much iodine-131 would be left over. Now, this is the part that you might be expected to do on the test. It says, predict the amount remaining 2 weeks after purchase. So in this case, I would give you this model, and you would just have to plug in the correct number and tell me how many grams would be remaining after a certain amount of time. So something, though, that I want you to notice here is that in our original model, they used days, but this is asking for the amount after 2 weeks. All right, so since our model was developed with days, we need to be plugging in a number of days, not a number of weeks. So let's convert weeks into days. We know that in 2 weeks there are 14 days, so we should plug in t equals 14. All right, so plugging in 14 for t, that gives you 20 times e raised to the negative 0.086643398 times 14. All right, and this is what it's going to look like once you plug this in your calculator. So 20, find your e button, so negative 0.086643398 times 14. Then close the parentheses if yours opens one up for you. And there you have it. It doesn't tell us what to round to, so I'm just going to use 2 decimal places. So y equals 5.95 grams. All right, so I'm using the units of grams because I know that in the problem it says that the hospital initially purchased 20 grams. So that sort of gives me a frame of reference for what my unit should be. All right, now let's look at a homework problem. So this problem also deals with iodine-131. And one thing I just want to point out to you is that they're using a different number here. So if you look right here, their decay constant, for some reason, they don't round up at the end. So I just wanted to point that out, just so you don't go use the same exact model that we just developed, because for some reason the homework is using a different number here. Okay, so it says, using the model Q equals 20 times E raised to the negative 0.086643397 T, predict how much iodine-131 will remain after 3 weeks. Let T be measured in days. Round your answer to 1 decimal place. All right, so we need to figure out how much iodine 131 is going to be left after 3 weeks, but we know that we're supposed to be plugging in days. So we need to convert 3 weeks into days. So 3 weeks is 21 days because there's 7 days in a week. So we're going to plug in T equals 21. And just notice here that I have adjusted my model so that my decay constant is correct based on what the homework wants. Alright, so I'm going to plug in T equals 21. That's what that would look like. 20 times e raised to the negative 0.086643397 times 21. And let's plug this in our calculator. So 20 times e raised to the negative 0.086643397 times 21. That gives you 3.242. Right, and they tell us to round to 1 decimal place, so this would be 3.2 grams remaining after 3 weeks. Now, this model that we've been using, y equals a times e to the bt, it can be used for exponential growth, or as we've seen in this video, exponential decay. So it says, in general, any quantity for which the rate of change is proportional to the amount present. So remember we saw that with exponential growth with the populations of people, and we've seen it here in this video with the amount of a radioactive substance that's remaining. So we saw that with exponential decay in this video. So they're saying that that can be modeled by the formula y equals a times e to the bt. Now the difference is that if your value of b is positive or greater than 0, then y is growing exponentially. But if your value of b is less than 0, or if b is negative, then y is decaying exponentially. So a really easy way to figure out if you're dealing with exponential growth or exponential decay is just you look at the value of b. Now, coming back to radioactive substances, something that you may have heard of before if you've taken a chemistry class is half-life. And half-life gives us a way to measure the instability of a radioactive substance. So the larger the half-life, the more stable that substance would be because it takes longer for it to decay. So it says the amount of time required for a quantity to reduce to 1/2 of its initial size is the half-life. So if you start with 20, we start with 20 grams. The half-life would be the amount of time that it takes for that substance to reduce to 10 grams. You're going to have a problem like this in your homework, and so I wanted to show you how to do it. It's really easy. It takes hardly any work. It gives you this little table of radioactive substances and their half-life. So you can see Krypton 91 has a half-life of 10 seconds. That means it's really unstable. So that means it's decaying very quickly. And then at the bottom, you can see plutonium 239. It's very stable. So it has a half-life of 24,400 years. So it takes a really long time for plutonium 239 to decay. Now, this problem is asking, how long will it take 40 grams of magnesium 28 to decay to the following amounts? 20 grams, 10 grams, and 5 grams. All right, so we're starting with 40 grams, and part A wants to know how long is it going to take for magnesium 21 to decay to 20 grams. So let's look at magnesium 28 on our table. It says the half-life of magnesium 28 is 21 hours. So if we started with 40, 20 grams is half of 40 grams. So that's the half-life is 21 hours. Then it will take 21 hours for 40 grams of magnesium 28 to decay to 20 grams. In part B, it wants to know how long will it take 40 grams to decay to 10 grams. Well, 10 grams is half of 20 grams. So if it took 21 hours for 40 grams to decay to 20 grams, then it's going to take 21 plus another 21 hours for 20 grams to decay to 10 grams. Or excuse me, for 40 grams to decay to 10 grams. So 21 plus 21 is 42. And then last, you can probably figure this one out from here. Since 5 grams is exactly half of 10 grams, it's going to take 21 plus 21 plus 21, which is 63 hours for 40 grams of magnesium 28 to decay to 5 grams. All right, next we're going to talk about the specific radioactive substance carbon, and we're going to talk about carbon dating. So radioactive substances like carbon can be used to determine the age of fossils and artifacts. I'm sure you've heard of carbon dating before. And this procedure is based on the fact that there are 2 types of carbon that occur naturally in living things. There's carbon-12, which is stable, and carbon-14, which is radioactive. And then I just have this picture here. William Libby is the person who developed the method of radiocarbon dating in 1949 while he was a professor at the University of Chicago. All right, so the total amount of carbon-14 in the environment is pretty small. There's only 1 atom of carbon-14 for every trillion atoms of carbon-14, or sorry, of carbon-12. And living organisms are able to maintain this ratio by intaking or drinking, consuming water, intake of air, and other nutrients. And so whenever an organism dies and they stop taking in water, air, and nutrients, the amount of carbon-14 starts to decay exponentially due to radioactive decay, the interaction of those protons, neutrons, and electrons. So what William Libby was able to discover was that by making extremely delicate measurements of the amount of carbon-14 and carbon-12 in a fossil or an artifact, scientists can determine the age or try to estimate the age of that atom that they're investigating. William Libby, along with the other people that he was working with, were able to develop this radiocarbon dating model by looking at the half-life of carbon-14. And it says, the quantity Q of carbon-14 remaining T years after the death of an organism that had an initial amount A is Q equals A times E raised to the negative 0.000120968 times T. Now, you're just going to ignore the stuff that's on the right-hand side. This is the only part that you're going to use. All right, so you don't have to use any of this stuff over here. All right, so just like we developed that model earlier, William Libby and his team developed this model. So just like we did where they measured the amount of carbon-14 that they had initially in a living organism, they measured the amount that was remaining. They knew a certain time frame, and they were able to discover this decay constant, which is negative 0.000120968. So let's use this model for an example. It says, suppose that we have 72 grams of carbon-14. Using the model above, predict how much carbon-14 will remain after T years. Now, this model deals with years. We can see that right here. Sorry, that circle was so terrible. Let me try that again. So this model is developed for years, and that's based on the half-life of carbon-14. So we are going to plug in our initial amount A is 72, and T at the time is 10 years. So let's plug those numbers in. So we have Q equals, Q is the amount remaining. So Q equals 72 times E raised to the negative 0.000120968 times 10. So let's plug that in our calculator. Let me start that over. So we have 72 times E, once again using that E button on your calculator, negative 0.000120968 times 10. And then close your parentheses if your calculator opened them up for you. So we can see that there are 71, or that we are predicting that there will be 71.91 grams of carbon-14 remaining after 10 years if we started with 72 grams. This first problem comes from the homework, and it references an article that I'm going to show you on the next slide. It says, as noted in the article on the Shroud of Turin, radiocarbon dating analysis concluded that the shroud was made in the 14th century. Assuming that the shroud was made in 1365 AD, how much carbon-14 did it contain when it was tested in 1988? All right, so here is the Shroud of Turin. This is the cloth that they believe that Jesus was wrapped in. Right, so you can see the impression that it left. I'll give you a second. You can pause the video if you would like to read this article. Recall that we have this formula for the quantity Q of carbon-14 remaining T years after the death of an organism that had an initial amount A. So there's the formula. Q equals A times E raised to the negative 0.000120968 T. Since we don't know the initial amount of carbon that was present in the shroud, the only thing that we can calculate is T. Right, so we're going to try to calculate the time that has passed. Now this should be pretty easy to calculate given that we know that the shroud was tested in 1988 and that the shroud was made in 1365. So we'll just do 1988 minus 1365. That's going to give us 623 years. Right, so now we know that T equals 623. Now let's plug in what we know, which is T. All right, so plugging in T equals 623, we have Q equals A times E to the negative 0.000120968 times 623. I'm not going to multiply that out just because I know it's going to give me a long decimal, so I'm just going to leave it like that. But what I need to do now is I need to divide both sides by A. This way we have everything that we don't know on one side, and we can just plug the right-hand side into our calculator. All right, so dividing both sides by A, that's going to cancel out the A's on the right-hand side. Now we're left with Q divided by A equals E raised to the negative 0.000120968 times 623. Now you're going to go ahead and plug the right-hand side into your calculator using the E button. And here I have just a screenshot of what that should look like. So we're left with Q divided by A equals, and I've rounded it to 3 decimal places, so that's 0.927. Now I need to convert that into a percentage because that's going to tell me the percent of carbon-14 that was remaining. So moving that decimal 2 places to the right, that tells us that in 1988, the Shroud of Turin contained 92.7% of the original amount of carbon-14 expected in a living organism. Now we have part B to this question. It says, Again, as noted in the article in the Shroud of Turin, radiocarbon dating analysis concluded that the shroud was made in the 14th century. However, let's assume that the shroud was made at the time of Christ's death in 33 AD. How much carbon-14 should it have contained when it was tested in 1988? All right, so the only difference in between this problem and the problem we just did is the number of years that have passed. So we need to recalculate t. Remember, t tells us how many years have passed. All right, so therefore, instead of having 1988 minus 1635, this time we're going to have 1988 minus 33, which is going to give us 1,955 years. All other calculations will be exactly the same. I'm going to give you a chance to pause the video now, and then you can check your answer and make sure you get the question right. And here is the answer. If the shroud was made at the time of Christ's death in 33 AD, 78.94% of the original carbon-14 will remain. And I think it looks like they wanted one decimal place, so I should have left that as 78.9%. Formula that we used in the last problem. So we have Q equals A times E raised to the negative 0.000120968 times T. Remember, Q is the quantity remaining, the quantity of carbon-14 remaining. A is the initial amount of carbon-14 that was present, and T is the years after the death of an organism. So we have to manipulate this formula a little bit. We'll algebraically manipulate it so that we can use what we know. So what we're going to have to do is divide both sides by A so that we can use the fact that we know that the scrolls contained approximately 79% of the expected amount of carbon-14. So dividing both sides by A, we get. Now, similar to what we did last time, we're left with Q divided by A equals E raised to the negative 0.000120968 times T. Now we're going to replace the Q of A with what we know about how much carbon was left in the organism. All right, so it says, since we know that the scrolls contain approximately 79% of the expected amount of carbon-14, the first thing we need to do is change that 79% to a decimal. So 79% as a decimal is 0.79. We're going to replace Q divided by A by 0.79. Now to get T by itself, since T is in the exponent, we need to take the natural log of both sides. Now this is something that we learned in class, and we learned that natural log and E are inverses or opposites, and they cancel each other out. So here we've taken the natural log of both sides. Remember that natural log and E cancel each other. So we're left with natural log of 0.79 equals negative 0.000120968 times T. So everything that was in the exponent has now come down, and it's become our right-hand side. Now the last thing we need to do is just get T by itself, so we're going to divide both sides by that coefficient of negative 0.000120968. Then go ahead and plug the left-hand side into your calculator. I've got a screenshot of what that should look like. And thus, now we can see that the Dead Sea Scrolls are approximately 1,948.6 years old. In 1947, that's how old they were. If you have any other questions about exponential decay, please feel free to email me. Otherwise, I'll see you guys in class.